Hello, ladies and gentlemen. Today I am going to explain what the Higgs boson and the Higgs field is all about, and I will also go through an example problem with you to wrap it up. So here is a picture of what matter interacting with the Higgs field would look like if we could see it. Now, the Higgs boson and the Higgs field go hand in hand, and the theory says that matter gets its mass from the way it interacts with the all-powerful Higgs field. In order to understand what the Higgs boson is, we should first talk about the way cosmos work, which is known as the Standard Model, right down to the fundamentals. So, for some time now, scientists and physicists have concluded that the universe is rapidly expanding and will continue to do so to the end of time. Ever since the Big Bang occurred, the universe has been rapidly expanding and the planets are accelerating away from the sun and will do so until we are in complete darkness and our planet ceases to exist. Now, particle physicists have dedicated their careers to discovering the building blocks of the universe. We discovered atoms, protons, neutrons, electrons, quarks, leptons, and the list goes on and on. And recently we discovered a new particle which behaved like the Higgs boson particle. Hasn't been confirmed yet. It was discovered at the Large Hadron Collider in Geneva, near Geneva, Switzerland, which is very exciting for physicists. And these discoveries have given us more insight on different types of matter and forces than any other theory in modern physics has. So the Standard Model was developed in the early 1970s. The theory said that our entire universe is made up of just 12 particles and 4 forces. The particles being 6 quarks and 6 leptons. And protons and neutrons are made from quarks, and the electron and electron neutrino are made from leptons. Now, the 4 forces are right here, and they were believed to exist, and they consist of the strong force, which binds the nucleus, right over here, the electromagnetic force, which bonds atoms, the weak force in radioactive decay, and finally the gravitational force that binds the solar system, discovered by our man Newton. However, this model was missing something, and we believe it is the Higgs boson particle. Physicists say that the Higgs boson is the final piece of the puzzle. Here is a beautiful simulation image. Isn't that beautiful? Higgs field. Now, us physicists and scientists believe that each one of the 4 forces have a corresponding boson that acts upon matter. Now, this sounds very complicated, right? But I am going to try my best to explain it in a very simple way. We generally don't think of something to exist unless we actually see it. But just imagine that forces are just like matter. You can't see it, but you know it acts upon something you can physically see. So let's say you are trying to carry, push, or pull an object. There is nothing in the surrounding here. There's nothing other than air, right? But it has some resistance to it when you're trying to move an object. That's why the bigger the object, the harder it is to move around. So why are bigger objects harder to move around? It's because bigger objects interact more with the Higgs field, and the Higgs field is everywhere. It's surrounding the entire universe. Now, let's take a look at these two carts over here. So the cart in figure B has a smaller mass, and the cart in A has a bigger mass. So A will interact more with the Higgs field simply because it has a bigger mass, and it will be harder to push through the invincible, all-powerful Higgs field. The size does not necessarily matter. It is simply the mass of the object. Physicists say that particles gain mass by passing through a field known as the Higgs field. They say that if the Higgs field actually existed, everything that has a mass on this universe gets its mass by interacting with the Higgs field. So this cart A would interact more interaction, and cart B, even if they were the same size, because cart A has a bigger mass, it would just interact more with the invisible Higgs field. So less interaction equals less mass. More interaction equals more mass. Pretty simple, right? Now, just like other fields covered by the standard model, the Higgs field needs a carrier particle to affect other particles, and this is what the Higgs boson particle is all about. In 2012, scientists at the Large Hadron Collider came across a particle that behaves like the Higgs boson is predicted to behave. At this facility, they are performing an experiment where they take particles and they make them go around the Large Hadron Collider near the speed of light, and they slam them into each other. Here is a picture of the tunnel itself. Now this is actually quite impressive. It is the biggest, most complex experimental facility ever built, and the largest single machine in the world. Very, very impressive. So now, when particles collide near the speed of light, they're essentially slapping the fabric of space-time. If the Higgs field actually did exist, then the field must be disrupted and slapped upon this collision. It's very, very difficult to come upon one of these. Here is a nice picture of CERN, the Large Hadron Collider. It's on the border of France and Switzerland, near Geneva. Okay, back to the slapping space-time. So it's very difficult to discover one of these Higgs particles. Now, they say it only happens in 1 in a trillion collisions, and in that collision, it will actually flick off a piece of the Higgs field and cause a Higgs boson particle to show up like this one. Now, let's just do an example to see the potential of the Higgs boson. So let's say that we have discovered the Higgs boson particle, and the mass is, so let's see, mass of boson is equal to 150 giga electron volts divided by the speed of light squared. And physicists believe that it may be the mediator of a new force. So let's use this mass to determine the range of the force. Here we have a beautiful equation relating so that we can use to find the range of the force. Range of the force is equal to Planck's constant divided by 2 pi times the speed of light, all divided by 2 times the mass of the boson times the speed of light squared. So now we can take the Planck's constant is 4.136 times 10 to the negative 15 electron volt seconds. Divide that by 2 pi multiplied by the speed of light 3 times 10 to the 8 meters per second. All divided by 2 times the mass of the boson, 150 giga times 10 to the 9 electron volts per the speed of light squared times the speed of light squared. And this gives us the range of the force of the Higgs boson if it were to exist, and we get 6.58 times 10 to the negative 19 meters. This is very small. Now here is we can compare this to the force range of, say, an electron. So the mass of an electron is mass of electron is 510,998.946 electron volts per speed of light squared. Now if we were to find the range of the force of an electron, that would give us, so calculating the range of force on this electron, we get 1.93 times 10 to the negative 13 meters. Notice how much bigger this is than the Higgs boson particle, and this is simply because the Higgs boson is the smallest part that makes up the Higgs field. My name is Nima Kianipour. Thank you very much. If you enjoyed this video, please subscribe so I can make more of them.